Welcome to this lesson on AP Statistics. Today we are exploring Topic 2.8, Least Squares Regression. Our objectives are to estimate parameters for the least squares regression line model and interpret the slope and y-intercept in context. By the end of this video, you will be able to calculate the equation of a regression line from summary statistics and explain exactly what those numbers mean in a real-world scenario. We have already talked about how a regression line models the relationship between an explanatory variable x and a response variable y. But why do we call it a least squares regression line? Recall that a residual is the difference between the actual observed value and the predicted value from our line. If we want the best line, we want these residuals to be as small as possible. The least squares regression model specifically minimizes the sum of the squares of these residuals. By squaring them, we make all the distances positive and give more weight to points that are far away. This mathematical criterion gives us a unique line that fits the data better than any other possible straight line. Before we start calculating, there is a very important property of the least squares regression line that you should know. The least squares regression line always passes through the point x bar, y bar. This means that the point representing the mean of the explanatory variables and the mean of the response variables is always a coordinate on our line. The general form of our regression equation is y hat equals a plus bx. In this equation, y hat represents the predicted value of the response variable. The letter b is the slope, and a is the y-intercept. To build this model from scratch using summary statistics, we need to find these two values. The slope, b, can be calculated using the correlation r and the sample standard deviations of our variables. It is the correlation multiplied by the ratio of the standard deviation of y over the standard deviation of x. This tells us how much y is expected to change for every 1 unit increase in x. Now that we have the slope, how do we find the y-intercept? Remember that we just learned the line must pass through the point of the means x bar and y bar. We can use this fact to solve for a. The y-intercept, a, is equal to the mean of the y values minus the slope times the mean of the x values. In terms of interpretation, the y-intercept is the predicted value of the response variable when the explanatory variable is exactly 0. However, you must be careful. Sometimes the y-intercept does not have a logical interpretation in context. For example, if you are predicting a student's height based on their age, the y-intercept would represent the predicted height at age 0. While mathematically possible, a height of several inches for a person who hasn't been born yet might not make sense in every dataset, or the data might not even include values near 0. Always check if x equals 0 is a reasonable value for your data before interpreting the intercept literally. Let us look at a numerical example to see these formulas in action. Suppose we are studying the relationship between the number of hours spent studying, which is x, and the score on a statistics exam, which is y. Here are our summary statistics. The mean study time is 5 hours with a standard deviation of 2. The mean score is 80 with a standard deviation of 10. And the correlation is 0.8. First, we calculate the slope, b. We use the formula b equals r times the ratio of the standard deviations. The slope is 4. This means for every additional hour a student studies, their predicted exam score increases by 4 points. Next, we find the y-intercept, a. We subtract the slope times x bar from y bar. The y-intercept is 60. This means for a student who studies for 0 hours, the predicted exam score is 60 points. So, our least squares regression line is y hat equals 60 plus 4x. Notice how we use the hat symbol over the y to emphasize that this is a predicted value, not necessarily an actual observed score. Another critical concept in linear regression is the coefficient of determination, denoted as r squared. As the name suggests, in simple linear regression, this value is literally the square of the correlation coefficient r. If our correlation r was 0.8, then r squared would be 0.8 squared, which is 0.64. This is the interpretation of r squared, the proportion of variation in the response variable y that is explained by the explanatory variable x in the model. This value is usually expressed as a percentage. In our exam score example, an r squared of 0.64 means that 64% of the variation in exam scores can be explained by the linear relationship with study hours. The remaining 36% of the variation is due to other factors not included in our model, like prior knowledge or how much sleep the student got. To recap, least squares minimizes the sum of squared residuals. The line passes through the point x bar y bar. The slope b is calculated as r times the ratio of standard deviations. The intercept a is y bar minus b times x bar. And r squared is the proportion of explained variation. We have now covered how to estimate the parameters of the least squares regression line and how to interpret those coefficients. You are now ready to tackle regression problems by looking at both the calculations and the logic behind the best fit. Happy calculating!